Oh, yeah, we didn't finish this. I gave y'all the answer on this first one, right? Let me show you how to work it. So we want to find the force on the 6 nanocoulomb charge. In order to do that, we say that F is equal to K Q Q over R squared. That's 9 times 10 to the 9th times Q, which is 3 times 10 to the minus 9 times 6 times 10 to the minus 9 divided by the distance squared. We found the distance up here is 0.71 meters squared. And that's equal then to what did I say the answer was? A? Okay, yeah, so 3.2 times 10 to the minus 7. So the answer is A. Now what about the direction of that force? So what I want you to do now is use your unregistered clickers to select the direction of the force. But you don't need a calculator, just think about it. Look at the triangle that we're dealing with, and then think about what is the direction. Be careful, though, how you measure that angle. Mackenzie. Oh yeah, so the 9 times 10 to the 9th, that's K. That's our Coulomb's constant. Okay. 3 times 10 to the minus 9, that's this charge, 3 nanocoulombs. Okay. And then the 6 is this charge, 6 nanocoulombs. Notice that I didn't use the negative too, right? That don't use that in Coulomb's law. All right, let's try to wrap it up by 15 seconds. It's a good indicator of what you'll see on the test as far as 2D fields, or 2D forces rather. We'll do some more before that test. I'm going to stop at 1:30. 1:30. All right, we're sort of all over the board, but the right answer is A. A is the right answer. Let me show you. First, I'm going to sketch in the vector. On the 6 nanocoulomb charge, that force vector looks like that. I know that it's up because it's a positive and a negative charge, and those are going to be attractive forces. Then I draw my coordinate system like this, and then I recognize that this triangle right here is an equilateral right triangle. I didn't learn much in 10th grade geometry, but I learned what an equilateral right triangle is, right? And I know that the angles in that triangle are what? What's this angle? It's 45. They have equal angles. So that's 45 degrees. If you forget, you just do the inverse tan of 0.5 over 0.5, and that's 45 degrees. And so now I go down here. I know it can't be 30 because that's no variance of 45. But is it 45 above the positive x-axis? Well, it's 45, but not above the positive x-axis, so that's wrong. It's also not below the positive x-axis, because then it'd be in the 3rd quadrant, right? To be below that, or no, it'd be in the 4th quadrant. So it's not that. So how can it be that answer? Well, it's 135 degrees counterclockwise from the positive x-axis, 135. And the way that I'd get that is I'd say 180 minus 45, that's equal to 135. Okay? We'll do some more of these. We're going to do more 2D vectors moving into electric fields. And then later, when we're sort of reviewing this chapter, we'll come back and look at some other little test questions. Okay? So you need to know how to do 2D vectors. You're going to see 3, 4 questions on the upcoming exam. Let's do a few clicker questions. So turn to the back of your book. Here I have two charges. This charge feels a force of 3 newtons. What is the force that this charge feels? All right, let's stop at 53. 53. Just guess if you're not sure, okay? Remember, you do get credit even if you get it wrong. Hey, look at you. That's awesome. Hey, what did the duck say to the bartender? Put it on my bill. All right, this is an application of which of Newton's laws? Right, the third law, that anytime I have one force, I have an equal but opposite force. Remember we talked about this. Did y'all go tell your friends? Hey, you want to know a cool application of Newton's third law? Electric forces. That anytime I have one electric force, I have another force somewhere else that's equal but opposite. Always, always, and forever. I think that's a Randy Travis song, isn't it? Always and forever? Or something? No, forever and ever? Amen. Right, yeah, okay. My grandmother used to say that I looked like Randy Travis. All right. Let's say I have this situation. I have two charges, Q and Q. I know that this force is 3 newtons, so this force is also 3 newtons. But what if I increase one of those charges by a factor of 4? What then is the force on this charge? All right, y'all doing really well. Just a few more seconds. Ask your neighbor. If you ask your neighbor, they got it right. Okay, so I'll stop at 45. Oh man, I'm sorry. It was 100% just a second ago. So C is the right answer. Look, F is KQQ over R squared. And if I quadruple one of these charges, then I quadruple the force. So where it was 3 newtons, now it's 12 newtons. It's a linear relationship. I don't have a joke for you, but I do have a funny story because it was just kind of, it was humorous. I went to get blood, like in one of those blood mobiles they bring up on campus. And you know, usually get blood. It's a good thing. It helps people. And so I went to get blood, and they typed my blood like they do, right? They prick your finger or whatever, and then they type it. And the lady, she doesn't usually tell me this, but she said, "Oh, you have type A blood." I'm like, "That's not right." "Oh, it's a typo." I do have type O blood, but that didn't actually happen. I was lying to you just now, deceiving you. All right. Okay, what if I have these two charges, they experience a force F. What if I separate them by 3 times the distance? So they were a distance D, now they're a distance 3D. What is the new force now? All right, let's stop at 53. 53. Okay, E is right. That's all right. All right, so this is an inverse square relationship. F is equal to KQQ over R squared. The relationship between F and R is an inverse square relationship. So if I triple R, then I decrease F by a factor of 9. Right, I put a 3 right here, and that gives me 3 squared in the denominator. So it changes my force by a factor of 1/9. So my force now is 1/9 what it was originally. If I move those charges farther apart, I get a smaller force. In fact, I get a smaller force by a lot. If I were to plot the force versus the distance, it would look something like this. It's not exponential, it's a quadratic formula, but it gets smaller as I go farther out. Oh, I like this question. I have two charges, plus Q and plus 4Q. Can I put a third charge somewhere in between here so that the force on that third charge is equal to 0? Can I do that? This isn't possible. And if it is possible, what about the sign of that charge? Positive, negative, what? So can I place a charge where the net force on that charge is 0? Think about how the forces add up. Feel free to ask your neighbor. Y'all are sort of all over the board, so ask your neighbor, but be wary. Cast them a critical eye, because they might have it wrong. A number of you have it incorrect right now. All right. Let's stop at 120. Just 5 more seconds. C is right. That it is possible to have that, but it doesn't matter what the sign is. So let's just imagine that I have a positive charge here. I'm not going to worry about the sizes of the forces, but the force due to the plus 4Q charge will be over here, and the force due to the plus Q charge will be in that direction. But what if it was a negative charge? Then it would be over here, I would have the force due to the positive Q charge, and then over here I'd have the force due to the plus 4Q charge. So it doesn't matter if it's positive or negative. I can still get a net force of 0 in between those two charges. Now let me ask you another question. This one isn't written down. But what if, or where, let's say that I have a plus Q naught. Where do I put it? Do I put it right here in the middle? Or do I put it somewhere between here? Or do I put it somewhere over here? So do I put it left of center, at the very center, or to the right of center? Where do I put that charge if it's positive, plus Q naught, so that the net force is 0? Where can it go so that it has 0 force on it? It seems just like an exercise, but it's kind of interesting because, like, what if I wanted an isolated charge? I had a charge and I wanted to hold it. Well, then I would put it in a place where it has 0 forces acting on it. Because if it has forces acting on it, it's going to zoom off. But if I can put it in a place where there are 0 forces, then it's going to stay put. Now, where am I going to put it? In section A, to the left of center, at the very center, or to the right of center? All right, let's stop at 105. 105. Okay, good. A is right. Let me show you. So if I have a positive charge plus Q, it experiences forces. It experiences a repulsive force from that positive Q charge. And then over here, it also experiences a repulsive force from the positive 4 charge. The reason I have to put it over here is because we want this force to be the same as this force to give us a net force of 0. But this is a bigger charge, so I got to get farther away from that charge, actually twice as far away from that charge, so that my force is equal, so that it's diminished. Because if I put it over here, what would happen? is I would get a force due to the plus Q charge in that direction. And then due to the positive 4 charge, it'd be really big because it's really close to that positive 4 charge in that direction. And so over to the right, and at the center too, I can't have net force equal to 0 because the positive 4 is always going to dominate the positive Q. So that seems like an exercise, but we'll see as we get into electric fields that it's actually kind of important. Taylor?
So that was negative or B and C, right?
That's right. No, that's wrong. Yeah, let's draw it. That's a good question. So imagine if I have a negative charge, then the force due to positive Q is going to be in this direction, and the force due to positive 4Q is going to be in this direction. They're still going to be they'll just be flopped, like opposite the direction they were. But I still want this negative charge to be far away from the big charge, so that this force is diminished and equal then to this force.
Didn't you, when you wrote the negative just before, that you had it the other way around? The positive was on the left and the positive 4 was on the right.
Yes, you're right. Let me fix it. Sorry. Yeah, so these are attractive forces. So this is F positive 4, and that's F positive. Right, they're attractive. You see what I'm saying? Because the force between these two charges, they're attractive. The force between these two charges are repulsive. Or excuse me, are attractive as well. So, but you still want to have it to the left. Okay? Y'all with me, people? These are good test questions, or something like them. Look back at the old test. You'll see some similar things. Hey, in fact, since you don't have anything to do this weekend, why don't you just print out some old tests? Because you'll see that a lot of what we've done, you'll see on the test. Coulomb's law, these things, we're just sort of thinking about charges. Just print out some old tests, or there are some in the back of your workbook, and work through 10 or 15 questions. That's a good idea. What happens to the force between this proton and electron as they move closer together? All right, let's stop at 40 seconds. 40? Okay, good. A is right. That as they get together, the force is going to get bigger, right? Because F is equal to KQQ over R squared. As R decreases, F increases. It's an inverse square relationship. It increases by a lot, in fact. Hey, it was kind of foggy out the other morning, and I went out. I was going to try to catch some, but I missed. But that was the punchline. Did y'all get it? Did you get the joke? Okay, you just didn't think it was funny. I missed. Like missed? Okay. All right. Which particle has the larger acceleration at any one moment? The proton or the electron? Or are they the same? We know they have the same force. As Newton's third law. All right, I'm going to stop at 30. Which one do y'all think it is? You missed. What do y'all think? A or B?
They're isolated, right?
Yeah, they're isolated. They're just out in space. No, it's not C. Why B? You're right. Right, protons are like 10,000 times heavier than an electron. A lot heavier. The larger acceleration is B. Oh, that's C. Yeah, it's the electron has a larger acceleration because it's a lot smaller. It's like a sumo wrestler versus like a second grade boy. Who do you think is going to get away? The second grade boy. He's a lot smaller. He can run around a lot faster than the big old sumo wrestler. Okay? Even though he's not as strong, he can just move a lot more nimbly. Oh, man. Well, there. They would meet closer to the proton side. Closer to the proton side because the electron is accelerating faster. The proton is sort of slow to get moving. All right, which one of these best represents the direction of the net force on charge plus Q due to these other two charges? We did one very similar to this. You'll probably have one on the test like this. Let your 1 through 5 be A through E on your clicker, please. Now let's stop at 40 seconds. Just a few more seconds. All right, good. B is right. Did y'all get the answers from the 3M section before you came in? Because y'all are doing a lot better than they did. B is right. Look, I have these forces. This force due to the plus 2Q charge is in this direction. Due to the plus 4Q charge, it's up in that direction. It's a lot bigger just because it's a bigger force. And so my net force will be off in that direction. Hey, where does bad light end up? Bad light end up. You know, light that's bad. Troublemakers. In a prism. That was a good one. All right. We'll come back to this. We're doing electric fields now, so we'll come back to this. Let's move on to electric fields. Took me a long time to figure out what an electric field is. Like, I don't think I really ever understood electric fields until I came here, I guess. And they're just kind of confusing. But they're not really confusing. Like, you'll get it because I'm going to tell you. We're gonna practice and things. You'll figure out what electric fields are. Electric fields, they aren't a substance. They're not some gas or liquid. Electric fields are closely related to the force. In fact, we just use electric fields to describe what a force is. So, like we have gravitational fields. The Earth has forces that act between bodies of mass, and we use the gravitational field to describe what type of forces those objects of mass encounter. And in a similar way, we'll use electric fields to describe what type of force charges encounter. So we're sort of building, we have Coulomb's law, and that describes forces. And then we're going to go up to electric fields, and that describes a force per unit charge. And then next we'll do potential, which is, what is potential, or voltage? Energy per charge, right. So field is force per charge, potential is energy per charge. So a field is just describing a force. It exists in the space surrounding a charged object, though it's not a substance. It's just sort of something that we make up. And we define the electric field in this way. Our electric field, this is our definition of electric field. Electric field is defined as, that's what the three lines mean, a force divided by Q naught. These are vector quantities, so the electric field is a vector just like forces are a vector. So notice that the electric field and the force, they're basically the same. The only thing that we have different is this charge. Because electric field, it is a force per unit charge. That's what electric field is. And we're going to use the electric field to describe the situation is, what if I bring a charge into this electric field, then what force will it feel? Here, Q naught is an imaginary test charge. It's imaginary. It has no value. It's also, I didn't write this, this is very important, it is an imaginary positive test charge. So it's some charge that has some positive value. It doesn't really matter what the value is. Don't try to assign it a value, because it doesn't even really exist. It's just in your mind. So I had a high school physics teacher, Helen Perry. I know Helen Perry. She's dead now, unfortunately. But she was an awesome physics teacher, and she was like a farmer woman, right? She grew up on a farm, she worked on a farm, she's talking about dropping the engine out of her tractor and redoing the piston or whatever, I don't know. But she was a tough old bird. But she used to talk about how you always carry two things in your back pocket, and this is good advice for you. You know what two things you carry in your back pocket? You carry the imaginary test charge, the imaginary positive test charge, and then you also carry your right hand. Remember the right hand rule? We did it a little bit last semester. We're going to do it a lot this semester. You're going to love me for it. All right. So you always carry your right hand in your back pocket. Look at y'all doing the right hand rule. Awesome. Remember that? Yes. All right. And then also your positive test charge. It's just an imaginary thing. The units of the electric field are newtons per Coulomb. And then also, I'm just going to give you this. You don't really know what this means, but electric field is often given not as newtons per Coulomb, though those are perfectly fine, but sometimes it's given as volts per meter. Volts is a measure of potential or voltage. All right, we'll see later when we get into potential that those are the same quantities, but either newtons per Coulomb or volts per meter. Now, when you have a charge within an electric field, then the force that that charge feels is equal to this, is equal to Q times the electric field. Now this is not my test charge. This just says if I have a charge within an electric field, then what is the force that it feels? So let's say that I set up some electric field. Super easy to create electric fields. And in fact, you can create very complicated electric fields very easily. You'll do that tomorrow or in lab, the second lab that you do. Let's say that I set up an electric field that looks like this. The arrows represent the direction of the electric field. And then I put a charge within that electric field. Let's say that charge has a value equal to 2 coulombs. And then let's say that the electric field has a value equal to 3 newtons per Coulomb. What is the force that it feels? What force does that charge feel? 6, right. I'm not trying to trick you. It's just Q times E. That's 2 coulombs times 3 newtons per Coulomb. And so that's equal to 6 newtons. So it experiences a force equal to 6 newtons. All right? We'll come back to the test charge. You'll see how that's important a little bit later. Maybe not today, but we'll certainly come back to it. Let's try this question. This one draws back on some stuff that we've done before last semester. You have a proton. There's your mass of the proton. I didn't give you the charge of the proton, but you should know the charge of the proton. It accelerates from rest in an electric field of 100 newtons per Coulomb, or volts per meter. Those are the same units. What is the velocity of that proton after 2 seconds? You have to do several steps. You have to find what is the force acting on the proton, what is the acceleration acting on the proton, and then what is the velocity of that proton after 2 seconds. Remember your Newton's second law, and then also remember your kinematics equations. I'll just write them up here. You could still see some kinematics questions, but they'll be very simple like this one, just sort of one-step kinematics. Your first step is to find the force. I know the electric field, and I know the charge. What is the charge of the proton? What is it? It's the fundamental unit of charge, right? Electrons and protons have the same charge, and so the charge of a proton is that 1.6 times 10 to the minus 19. So find your force. F is equal to QE. Then use Newton's second law to find the acceleration. Remember Newton's second law, F equals ma. So what is A equal to? And then once you find the acceleration, then you want to find what is the speed of this object after 2 seconds. Minutes on the test, okay? I'm going to complete this in 2 minutes. All right, let's do about 15 more seconds. They're doing pretty well, those of you that have answered in. I'm going to stop at 320, okay? 320. Just guess if you're not sure. Ask your neighbor. Toss a coin. All right, B is right. B's pretty good. So find the force first. That's 1.6 times 10 to the minus 19. That's on your equation sheet. I won't usually give that to you. Just know the electron and the proton, they have that fundamental unit of charge. The electric field is 100 newtons per coulomb, or volts per meter. So that's 1.6 times 10 to the minus 17. That's in newtons. And then to find the acceleration, it's F over m. 1.6 times 10 to the minus 17 newtons divided by the mass. Here I gave you the mass, but I won't always give you the mass. It's on the equation sheet though. Make sure you use that as you're practicing and doing homework. In fact, usually I won't give it. I don't know why I did here. And then that's equal to 9.6 times 10 to the 9th. Meters per second squared. And then if I want to know the velocity, it's just the acceleration times time. And so that's 9.6 times 10 to the 9th times 2 seconds, which is equal, what was it, B? Yeah, B. 1.9 times 10 to the 10th. Several steps there. They're all things that you've seen before, except for that very first part, the F equals QE. That if I have a charge in an electric field, it feels a force. It experiences a force. And I can use that force to move that charge around however the heck I want. It's actually a very nifty thing to be able to move charges around. You can do some cool stuff with moving charges, right? Like you can power lights, and you can power projectors, and your cell phones, and all sorts of things. All right. Okay, so Coulomb's law gives the force between the charge and the test charge. So imagine that I have a positive charge here, and then I have a positive test charge. This is my imaginary positive test charge. The one on the left is a real charge. The one on the right is just something I make up in my head. But if I want to know the force between these two, I use Coulomb's law. Say F is equal to K, Q times Q naught divided by the distance between them, R squared. Right, the distance is R. So that's my force. That's Coulomb's law, what we've seen already. I also know from my definition of the electric field that F is equal to the force that the positive test charge feels is equal to Q naught times E. We'll see later, we'll represent the electric field as some arrows. We'll see that there is a field of forces that extends outward from this positive Q. And that those field of forces interact with this charge and cause it to experience a force. And that's how we define that on the right, that F equals QE. Now we can combine these two because these two are both equal to F. We can combine them and get an expression for the electric field. So the electric field is equal to KQ over R squared. So we have a couple of different definitions for E. Let me just write them out. First, we have that E is F over Q, but then we also say that E is equal to KQ over R squared. So that this second one tells us what is the electric field at some point far away, or a distance R away from a charge. And you'll see why that's important later. We'll do some calculations and some practice problems where we use that. But for now, I'm just going to leave that here. I do want to show you, though, that what do you not see in this expression for the electric field? What's missing from it? What canceled out? Q naught, right. Q naught canceled out. That's the charge of the imaginary test charge. It's a good thing that it canceled out, right? Because we've already said it's not a real thing. It's not physical. It's just something that we make up in our head. So notice that the electric field is in no way dependent upon the positive test charge. We just use this positive test charge in the way that we think about what the electric field is. But it doesn't actually exist. And it's not affecting the electric field at all. So the electric field is not dependent upon the test charge. The test charge is only a tool we use to describe the electric field. That's Q naught. Is only a tool to describe the electric field. Now, the sign of the charge Q determines the direction of the electric field. The direction of the electric field is the same direction. I'll show you with a picture what I mean by this. Let me just write the words. Same direction of the force felt or experienced by the positive test charge. So for example here, I have two charges, one negative, and then I have Q naught, which is positive. It experiences a force that's attractive. Right? So the force that is exerted onto that imaginary positive test charge is in that direction. And so the electric field, similarly, is in that direction. It's the same direction as the force. Over here, the force is in that direction. So what do you think the electric field is? To the left or right for the second scenario? It's to the left. It's to the right. It's the same as the force. Goodness, I'm teaching two back-to-back classes. It's kind of difficult, but just to keep going for 2 hours, but you high school teachers, who's my high school? Who my second person in this class? Man, I don't know how you do it. Like, how are you going to go all day? Because you like what you teach. I mean, I like it, but just physically. It'll be okay. You'll get the hang of it. Maybe next week. Awesome, or whatever. So anyway, we find the direction of the electric field. It is the direction of the force that's exerted on that object. Don't worry about it. We're going to have lots of practice with that. So we can, let's say that we have two parts, a positive Q1 and a positive Q2, and I want to know what is the electric field at this point. Now, I take my positive test charge out of my pocket, and I put it here, and then I ask myself, what is the direction of the force that this charge feels? And it's going to feel two forces. It's going to feel a force F1 that's in that direction, and then it's going to feel a force F2 that's in that direction. That's nothing new. But if we wanted to imagine what is the electric field, we can take away that positive test charge because it doesn't really affect the electric field, and my electric fields are going to be exactly the same. E2 in that direction and E1 in that direction. Look, we're moving into a direction where we're going to do exactly the same thing as we did for Coulomb's law, where we're going to have to calculate what is the magnitude of the electric field, that's that K2 over R squared bit that we did, and then figure out the directions of the electric field like this, and then we do a vector sum of the vectors to find the net electric field. So here it's easy because it's all along one line. Mackenzie?
Does it matter which side the one or the two go?
It does matter very much. You have to ask yourself, what are the directions of these forces? And then the electric fields are exactly the same. The electric field and the force on the positive test charge are always going to be the same.
How do you determine, like, you know, like F1, F2, like, does that matter?
Right, how do we do this? Well, we say these are two positive charges, so they're going to repel one another, so F2 is repulsive. Here, these are two positive charges, so they're going to repel one another, just like we did before. All right, so the net electric field, the sum of all the electric field vectors is going to be E1 minus E2. The vector sum, not just numbers. Though here, you know, they're on a line, so we do just add the numbers. And then if the charges are identical, the net field is what? Is equal to 0. Because E1 and E2 will be equal to one another. Let's watch a little video I have. Electric fields are very useful. Like, electric fields can be used in treating diseases, and that's the video that I have for you here, where they use electric fields to treat cancer. They're called tumor treating fields. Super simple to set up an electric field. If you're going to do it in the lab, all you need is just a limited power supply and some metal plates, and boom, you got an electric field. It's really easy. And then just with a little more work, you can make very fancy electric fields. You can make electric fields that have all sorts of different shapes and different magnitudes at different points in space. You can make an electric field to look however you want, basically. And so these electric fields can be used to treat diseases, and that's what this is about. These electric fields for other things too, right? Like you marine folk, you go out and you zap the fishes, right? You zap them. They do.
Not anymore.
They also do it, right?
Yeah.
Yeah, they zap them. They have this thing, they stick down in the water, and the fish, it just stuns them. They don't die. But they float up to the surface, and then they net them and bring them all in. I mean, then they die, and you cut them off, and you all that, right? Right. Okay, so electric fields are important for a lot of different purposes. Electric fields are present in our body, too, in the cells and within the nervous system. So electric fields we use to describe a lot of things. But let's watch this video.